Alrighty. So we just got finished with chapter 7. We're going to go through chapter 8 and then on to an exam. Today and over the next 2 lectures, we're going to just be doing one section of chapter 8 at a time. And so these lectures end up being a little bit short, almost every time. So, since we're almost at the final week, I'll be in my office and available for tutoring right after class every day. I would suggest that you guys use this time to catch up on any assignments you might be behind on, if you want to, or to study. Actually, I shouldn't say if you want to, just do it.
Just do it.
Yeah. Right? You must study. All right, so today we're going to go over the basics of square roots. And then tomorrow we're going to learn how to simplify those things and some more stuff. It's really the homework on this chapter it's pretty quick, like to simplify these square roots and to rip through these, especially on the ones where it just asks what the value of a square root is. Those I don't even need any work on those necessarily. And I forgot one of my handouts in my office. Darn it. I had a handout of the first 100 squares or whatever. I'll bring it in next week, or you can come to my office afterwards and get it. Okay. So what is a square root?
Something times something.
Yeah. That's a little unofficial, but yeah, it's not a rigorous definition, but I like that one. Yeah, a square root, right, means that if you have some number, c, and when you square that number, it equals a, c is the square root of a.
I see.
This is the symbol we use to denote square roots. It's called the radical. So let's just recall something about when we square 3. When we square 3, we end up getting 9, right? So the square root of 9 is 3. But also, when we square negative 3, we get 9. So negative 3 is also a square root of 9. So when we talk about giving us the roots of 9, we want the positive and negative version. Usually when we're talking about the positive version, we're talking about the principal root. And pretty much always when you see like a square root sign and just a plain number, like the root of 49, I'm pretty much always talking about the positive version of this, unless I say it's the negative version, or unless I have a negative sign out front. Okay, so for this one, they're saying find the square roots of 49. So it's saying find them both, right? So what are the square roots of 49? Plus and minus 7. There we go. Those are the 2 square roots of 49. What about this one? What are the square roots of 225? Right? Plus and minus 15. For this next one, so we're going to stop doing both roots now. We're just going to talk about the principal roots. Right? And so that's because we need to figure out what it means to have a negative sign out front here. All right, so when I have this, I haven't been asking, suppose the questions haven't been asking for roots. They just talk about, show us the value of this. We assume that the root of 64 is the positive version, and we just keep this negative sign out front. So I have negative 8 here. Okay, so more definitions. A radical expression, that's an algebraic expression that contains at least one radical sign. The radicand in each radical expression, that's just the part underneath the radical sign. So in this first example, they ask me to identify the radicand. So for this first one, I say the radicand is just x. For this second example, though, remember the radicand is everything under the radical sign. So the radicand for this one would be y squared minus 5, the whole thing. Okay, so just recall, and this is the first section of the chapter, so we're kind of bouncing back and forth between a lot of definitions and rules right now. But just recall real quick that the square of any real number is going to be positive. Okay, even if that real number starts out as a negative, like here I can square -6 and I get 36 as a result. And so if you square any real number, the result is always going to be positive, no matter what. Which means when they ask us to give a number that when squared equals -25, this isn't possible at this level. Okay, so we don't know a number that will do this right now. They exist, but in an imaginary realm that you guys probably never want to hear about, ever. So we can say no solution. We can say does not exist, DNE. We can say not real, anything that indicates that this is not a defined number. What about this? Is this defined? Think about it. Or do we have enough information yet? We don't have enough information yet because we don't know what x is equal to, right? If x starts out as just a plain old number, if x equals 3, then no, this whole thing is undefined. But if x equals -3, then we have a double negative, which makes this defined. Right? And so you can't really tell if this is necessarily defined right off the bat. But later on, not in this class, but next year, you'll learn how to restrict values for square roots as well, and not just denominators. But just so you know, this one, it could be defined, it might be defined, it might not be defined. It just depends on what x is, right? And so for this one, we could say, like, that's defined as long as if x is less than 0, that'll be defined. Okay, so let's talk about irrational numbers. These are some of my favorite numbers. Irrational numbers, these are numbers that cannot be represented as a ratio of integers, right? So there's no fraction that can represent an irrational number. Root 2 is irrational. That means there's no fraction of integers that can represent root 2 at all. Root 9, however, this is not irrational. That's because root 9 has an even square root of 3. So that leads to kind of the rule of rationality and irrationality. The rule basically says that the square root of any whole number is irrational unless that whole number is a perfect square, right? And so 9 is a perfect square, which means that its root is not irrational. Its root is just 3. So here's a little picture of the square roots of the first 25 numbers. And you'll notice here the only ones with perfect squares are these ones that are in black. And so you'll see there's far more irrational square roots with the whole numbers than there are perfect squares. Right? There's only a few perfect squares in those first 25. And that pattern kind of continues like that. Okay. And if you'd like to have kind of more of a diagram list of these numbers, I do have them in my office, and I'll bring them on Tuesday. Suppose I'm asked to classify each of these numbers as rational or irrational. Let's take a look. So, what about this first one? Square root of 10. Is 10 a perfect square of any number? No. So, like right there, we don't even have to do any more work. We just say irrational, right? Because 10 does not have an even square. If you're not sure if 10 has an even square and you've got a calculator, figure out how to use your square root function. It's really helpful on this part. Because if you're not sure, 10's pretty easy to figure out, but when you're getting up into the higher numbers, it's much easier just to say, well, what's the square root of 10? And when your calculator spits out some weird number that's not a whole number, you can say that's irrational, definitely. So this next example, what do you think, rational or irrational? Rational. Rational, yeah. Because this just equals 5. Oops, and here, let me erase this. This just equals 5. And because it has that nice whole number solution to it, it's rational. Careful on this one. What do you guys think this one is? Good. Yeah, it's rational. It's just rational. Because it just equals -3. -3 is a rational number. It's a whole number. So this is rational. Okay. Suppose we're asked to use our calculator to approximate root 10. Does anybody not have a calculator out there right now? First person in front of here, you can use this to learn how to take the square root of 10. Everybody should learn this, right? I know, it's weird. If you have your calculator right now, try it out. So for at least the calculator that you've got, Cheyenne, to access your square root function, first you hit this little second button, right? That accesses all the little blue symbols above the button. Then you punch in this button. It's got a little square root on top of it. Right, and so that should open up a couple brackets. Then you could punch in 10. There you go. Yeah, and you got some weird number, right? Sometimes with certain calculators, they make you punch in the number first and then hit the square root button. So not all calculators work in this order. Make sure you figure out how to do this on your own calculator, though, because it's really helpful. The phone doesn't work as well, though, because you can't use it in a test, right? And you don't want to be trying to learn how to use your calculator in the test. You want to learn how to use that before you go to the test. So after I punch all that in, this is what comes up on that calculator. It's 3.16, blah, 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 blah. Clearly not a whole number, so this must be irrational. And at least on this calculator, you know, if you've got one of these TI calculators, you can actually type in a whole equation if you want to in there. And so notice how I have this in this calculator. What that symbolizes, right? I'm calculating 10 minus 22 times a -5. So you can punch all that in underneath the square root as long as you close it off with a bracket in the end. So there we go. That's how you would estimate the root of 10. And actually, maybe we should just go ahead and estimate it. So we'd say root 10, and I give my little squiggly lines because that means approximately, is approximately equal to 3.16. Okay. Did everybody were you able to figure out how to use the square root? Yeah, you got it? Okay. All right. Good. So next, square roots and absolute values. So we're still bouncing around here a little bit with all this square root stuff. So let's talk about something that the square root does here. So let's just recall something that we've gone over a couple times already, that the square of any number is positive, right? So you can see here the square of 5, oops. Oh, okay, I'm sorry, I wrote this. Got a little too excited there. So just recall, right, that if we have 5 squared underneath the radical, right, the 5 pops out, right, because 5 squared is equal to 25, and so this comes out the other side. When we have a -5 squared, the same thing happens except for the negative is gone. Right? And so what this square does when you have the square root of something squared, the effect of that is just turning it positive. So basically, the official rule says that the square root of anything squared is the absolute value of that thing. And remember from the beginning of the class, absolute value just means the positive version, whatever that is. If it's already positive, it just stays there. If it's negative, the negative goes away. Typically in this class, this is a good thing to remember But next year is when this is really going to come in to be a big deal. We'll do a couple exercises with this, but for the most part, when you're doing these things, you can just kind of assume that all of your variables represent positive numbers. So let's go ahead and just try this out with this first example, though. Suppose we didn't say that all these variables represent non-negative numbers. When they said, simplify this, we'd say, well, this is the square root of 3x squared. So that must just give us the positive version of whatever 3x is. So we say absolute value, 3x. That's it. All right, don't overthink those ones. You just put whatever's inside the square in the absolute value. All right, so now if we assume that all variables represent non-negative numbers, we can stop using the absolute values, right? And this is what we usually do in algebra. The absolute values are something that pop up every once in a while, but they're more of a nuisance. This is usually how we do these. So if you ever see something, right, we have the square root of 8x squared. So the only thing that pops out is 8x. That's it. All right, and it doesn't really matter what is inside these parentheses. As long as it is the square root of something squared, whatever's inside those parentheses pops out. And so we have a sum here. That doesn't matter. It still pops out the other side, t plus 2. Right? The square goes away and the square root goes away. Okay?
You have to show the absolute value sign unless it specifies it's a non-negative number.
Yes. And in future chapters, don't worry about specifying that's a non-negative number. In this chapter, pay attention to the absolute values, but in the next chapter, it's don't let it confuse you too much. Next year, they'll hit you with it a lot. All right. So any questions about those ones? Right? It's basically like these two operations just undo each other. That's it, right? Taking the square root of anything squared, it just undoes everything, right? The only thing that it might do is just turn everything positive if it's a negative in the first place. But for the most part, if you have the square root of something squared, that thing just pops right out. All right. Now, sometimes in this first section, we are asked to calculate things. These are usually basic evaluation problems that we have here. I'll just steal my calculator back for this one, definitely. So for these ones, these are all just plug and play, especially in this chapter. So let's check out this problem. The attendants at a downtown parking lot use spaces to leave cars before they are taken to long-term parking stalls. The required number n of such spaces is approximated by this formula. N equals 2.5 times the square root of a, where a is the average number of arrivals in peak hours. Find the number of spaces needed when an average of 43 cars arrive during peak hours. Okay, so for this first one, they've already defined it. They said let a equal 43. So we just plug in a equals 43 and see what we get. So we have n equals 2.5 times the square root of 43. Whoa, got a little excited there. Square root of 43. I'm just going to punch all that into my calculator. 2.5 times second the square root of 43. Anybody else try that?
Yeah.
What'd you get?
16.397.
Excellent. This equals roughly 16.394. So we'd be tempted to leave this as is and just call this the answer, but they talked about the number of parking spots we should have open, and we're not going to open 0.394 of a parking spot. That's just goofy. But we want to round in the right direction. So if we're talking about the number of available parking spots, do we want to round up or down?
Down. Down. It's less than 0.5.
Careful though. We're not thinking about the mathematical rules of rounding. We're thinking about the reality of this problem. If they end up with fewer spots than they need, are they in trouble?
Side of caution and throw in a couple extra.
Yes, we want to round up one spot. Exactly. You want to analyze the problem a little bit. So we're going to say, yeah, the exact value is 16.394, but we're going to say, you know, leave 17 spots open. Okay. Let's do this for what if the average number of cars was 35 instead. So then we'd have n equals 2.5. This time it's times the root of 35. Why do I keep doing that? It's times the root of 35 instead. So let's see this. 2.5 times. Well, I got about 14.8, we'll say. Anybody else get something like that?
Yep.
Yes? That sounded like a yep. Okay, good. All right, and once again, we're going to want to round up because that's what the reality of this problem wants. Some problems force you to round down, but this one forces us to round up. So we would say they'd leave 15 spots open. So,
So when you're writing all this down, if you're some kind of math guy and math job doing parking spaces, would you use the exact number or the square root?
it depends on where you worked. Like, you know, if you worked at like Avis, you were like their math guy, probably wouldn't matter. Yeah, it just depends on what they would prefer. My guess is if they were just talking about parking garages, they wouldn't care about any decimals. They just want you to give them the number every day, right? Parking lot attendant's not going to want to read decimal places from you and then read them up. He's going to want you to do that. And so, yeah, you're going to want to give him that number. You know, on a more like, you know, on a more scientific job, like, you know, where we were supposed to maybe record the average values for some, I don't know, some scientific experiment or something like that, you know, maybe we'd want to round and then save all the exact numbers as well.
So for the answer for number 73 in our homework, I write it depends.
I don't know. What's number 73 in the homework?
What's the more exact way to write 12? 3.464177 square root of 12.
Ah, that is an excellent question. But that's not the question you asked.
I was trying to be subtle.
Very good. Well, I don't know. So riddle me this, and this should solve everything. Why do we write this?
Because it's not quite the exact answer.
Right. Is this the exact answer, though?
Yeah.
Yes. So there you go. So the most exact way to write root 12 is to write this symbol. Is that what the question? That's what the question was, right? No, not at all.
It didn't want to know if the approximation answer versus the square root was more accurate. It was just the full number written out.
The full number written out. Hold on. Let me check what number this was. 73. In what?
497.
497.
Because I don't know the answer, because they both seem exact.
497. What number is it? 73. That totally was the question that I just. Yeah, it's root 12. It's this one.
Well, there wasn't any approximation sign in that answer.
Oh, yeah. I'm sorry. That the approximation. I guess I was highlighting that we use the approximation sign to let everybody know that what we're about to write over here on this side is not as exact. I should have explained that a little better. I'm sorry. So yeah, if you ever want to be more exact, the root is definitely the most accurate. What the hell is that?
It's a trumpet. Someone played a trumpet out there?
I thought that was super weird. I thought it was Jafina's phone for a second, and I was like, that's the weirdest phone I've ever heard. That was strange.
was listening to the lecture from a few days ago, and my ringtone starts blasting.
So Noelle actually brings up a really good conceptual point. Irrational numbers, the numbers that we're talking about here, you can never write an exact version of an irrational number by listing decimals. It's impossible because they keep going. Because they just keep going to infinity, right? But if you write square root of 12, then you just know that's all the decimals included. Yeah, that's tough. That's tough. Right? I wonder if they can hear the trumpet. I should hang this out the window and give everybody a show. Just kidding. Oh, now I ruined the technology. What just happened?
It's a good thing we land.
So, I was going to blab at you guys about something else real quick before I let you go.
This is where you tell us you're not mad at us, you're just disappointed.
No. So I was going to tell you guys about an interesting concept about the real number line. So the real number line, right, here's 0, this goes to negative infinity, this goes to positive infinity, right? When we talk about rational and irrational numbers, they all take up different points on the number line, right? If we're talking about rational numbers, some of the rational numbers are numbers like 1, 2, 3, 4, whatever. More of the rational numbers are things like fractions, right? Which take up the space in between all of these, right? We could zoom in here.
Whoa.
These are all rational numbers in here too, 1/2, 1/3, 1 1/4, something like that, right? Sorry. Right, so this number line is it's filled with rational numbers. But if you choose, there are so many more irrational numbers than there are rational. If you choose a point anywhere on the number line at random,
Odds are it's gonna be irrational.
it is 100% to be irrational. You have a 0% chance of hitting a rational number. That sounds crazy. It sounds crazy because of the natures of infinity. There are multiple levels of infinity, right? The rational numbers are the first level of infinity. They're called countably infinite. So you can go from 1, 2, 3, and the next. The irrational numbers are so dense, they're called incountably infinite, which means there's an infinity more numbers in the irrationals than there are the rationals. And that's what makes that probability drop to 0 when you say, I'm just going to throw a hanky anywhere on, I don't know why it's a hanky, anywhere on, I'm going to throw a horseshoe anywhere on the number line and see if I hit a rational number. The odds technically are 0 that you do.
You don't want to throw a horseshoe because being close enough is good.
Hand grenade then. Just kidding. You know that saying? Yeah. So suppose you'd throw a dart. Yeah. Yeah, but that's just a little glimpse for you into the natures of the two infinities, right? One is so large, it's uncountable to our means, right? And that is the number line has uncountably infinite amount of numbers on it. And that's how weird mathematicians are. It turns out there aren't just those two first levels of infinity. We went ahead and we created an infinite number of infinities to build off of. However, we don't have anything to relate the higher levels to, right? I can sit here and tell you, well, the irrationals are a higher level of infinity, but as we get higher than that, there's nothing to relate them to. It's completely abstract, weirdo math people land.
You created your own multiverse. Why did that come out?
Yeah.
Who thought that was native?
Who, what?
Who thought that was native?
Mathematicians. That's one of my favorite things about mathematicians is that I say we like I did the infinity thing. No, people like that do things like just for the heck of it, and it's one of the concepts that really stuck me to mathematics the most. It was like, why? Because it's weird, and we want to see if we can. I even got the symbol for the nth level of infinity tattooed on my leg. It's a great concept to me.
Fun fact.
Yeah. Yeah.
People like to read a book.
Like,
Other
why did you
people
do
like
that?
to be different.
Why not?
Yeah, it's just fun, right? Okay, so that's it. Thank you for your patience today. You got quite a bit of extra time to use for homework if you feel like it. I would do that.